Section: Introduction. In this section, we discuss how we align generative language models using a method called KL Regularized Reinforcement Learning, KLRL. This approach is commonly used to fine-tune models to enhance certain rewards, like safety or quality. Typically, we start by training a reward model and then apply a reinforcement learning solver. There are also other methods to tackle KLRL, such as direct preference optimization and reward model distillation. We measure the success of our aligned model by comparing its win rate against a reference model on specific tasks. This win rate indicates how often our aligned model produces better samples than the base model, judged by a specific criterion. However, during inference, we usually employ various procedures, such as best-of-n sampling or chain-of-thought reasoning, rather than using the aligned model directly. This creates a gap between the inference process and the KLRL training objective, which aims to maximize the expected reward function. We pose the question: can we align a model to optimize its win rate during inference against a reference model? Although directly optimizing this win rate seems challenging, we introduce a framework called Inference-aware alignment, InfAlign, that captures the optimal solution through a set of optimization objectives. We demonstrate that for a specific type of language model, as certain conditions approach zero, we can achieve the solution by transforming the reward and applying KLRL. To address the inference time win rate, we design a reward transformation tailored to the inference procedure and use existing optimization algorithms like PPO. We focus on two popular inference strategies: best-of-n sampling and best-of-n jailbreaking, which we refer to as worst-of-n since it assumes the worst outcome is chosen. Despite their simplicity, these methods are effective for inference time alignment and safety evaluation. We solve InfAlign for various values of n, showing that an exponential reward transformation is nearly optimal for these strategies. We also find that using KLRL without reward transformation leads to suboptimal policies for inference time win rates. Based on our theoretical insights, we propose a practical solver called Calibrate and Transform Reinforcement Learning, CONTROL, which follows a three-step process: calibrating the reward model scores, transforming these scores for the inference procedure, and then solving the KLRL problem. We apply control to datasets focused on helpfulness and harmlessness, optimizing for both best-of-n helpfulness and worst-of-n harmlessness. Our results indicate that the exponential reward transformations we derived theoretically perform well in real-world tasks, surpassing various KLRL solvers in terms of inference time win rates. Additionally, we show that control, even without reward transformation, serves as a strong baseline for optimizing the win rate versus KL trade-off. In summary, we present the InfAlign framework for inference-aware language model alignment, demonstrating its theoretical foundations and practical applications. We derive optimal conditions for alignment in simple settings and reveal that the optimal solutions for best-of-n and worst-of-n are independent of the base policy and reward model, allowing for offline iterative optimization. Our empirical results on the Anthropic datasets show that control achieves competitive performance and improves inference time win rate versus KL trade-offs significantly. Section Summary. In this section, we introduce the Inference-aware alignment, InfAlign, framework, which optimizes generative language models for inference time win rates by transforming rewards suited to specific inference procedures. We also propose the Calibrate and Transform Reinforcement Learning, CONTROL, method, demonstrating its effectiveness in improving performance on tasks related to helpfulness and harmlessness while outperforming existing KLRL solvers. Section: Problem Setup. In this section, we consider a generative language model that generates responses based on an input prompt. For a given prompt, like, "What is a large language model?" the model produces a response that is drawn from a specific distribution based on that prompt. We denote the set of possible inputs as X and the set of possible outputs as Y. We refer to the distribution created by the language model as a policy and assume that our base policy is fixed, typically obtained through supervised fine-tuning. When we process information during inference, we often do not simply sample from the model. Instead, the sampling follows a modified distribution influenced by the aligned policy and the inference method used. For instance, if we use a specific inference method, we can show that the resulting sample is distributed in a way that depends on both the model's policy and the inference method. We model this inference process as a transformation that maps our base policy to a new distribution. To evaluate the performance of different policies during inference, we define an inference time win rate, which compares how well one policy performs over another under the given inference method. Our main goal is to maximize this win rate while adhering to a specific optimization problem that incorporates a KL regularization term. We propose a framework to tackle the language model alignment issue by designing a new reward function based on the existing reward model, the inference method, and the base policy. This new reward function allows us to solve the optimization problem effectively. We assert that for any inference method, we can find a reward function that leads to an optimal solution for our alignment problem. We also identify properties that the reward transformation and the resulting optimal policy must satisfy. If the transformation is well defined, we can derive a set of equations that the optimal reward and policy must fulfill. However, we recognize that our iterative approach to updating the policy and reward has limitations, particularly in terms of efficiency and the potential to reach an optimal solution. To improve our reward transformation design, we explore scenarios where no inference method is applied. In this case, the reward function simplifies to a calibrated reward based on the base policy. We find that when no inference method is used, our solution aligns perfectly with the optimization problem we set out to solve. This insight encourages us to investigate a range of reward transformations based on this calibrated reward, which we will discuss in the next section. Section Summary. In this section, we outline a framework for aligning generative language models by formulating a KL regularized reinforcement learning problem that incorporates a transformed reward function based on the base policy and inference time procedure. We demonstrate that this approach can effectively solve the language model alignment problem, even under various inference time transformations, and propose efficient methods for designing these reward transformations. Section. Towards solving InfAlign. In this section, we outline our approach to solving InfAlign. We begin by discussing some properties of reward calibration, followed by demonstrating how this method allows for efficient evaluations of various transformations for calibrated inference time procedures. We will illustrate the effectiveness of this approach using best of n and worst of n as examples of post hoc procedures. Any missing proofs can be found in the appendix. We start with the concept of calibrated reward. We assume that we have already obtained the calibrated reward and will explore methods to approximate it. One key property we note is that reward calibration maintains the order of rewards, meaning the win rate remains unchanged under calibrated rewards. This calibration is a limited, steadily increasing transformation of the reward, and the calibrated reward falls within the range of 0 to 1. Additionally, we find that the calibrated reward is a standard transformation that remains unchanged under any steadily increasing transformations of the reward function. This is beneficial because as long as our learned reward model captures relative human preferences, the calibration will remain consistent, making it more robust. Another important property is that the calibration process can convert the reward distribution from the base policy into a uniform distribution over the interval from 0 to 1, regardless of the base policy or the reward model. This gives us a clear, unified perspective on the output from a language model through the lens of calibrated reward. Next, we discuss how we can apply the calibrated reward in KL regularized reinforcement learning. After calibration, the reward distribution becomes independent of both the reward model and the base policy. This independence allows us to design a transformation function that focuses solely on the inference time procedure, without being affected by the base policy or the reward model. For a specific inference time procedure, our aim is to create a suitable transformation that balances the inference time win rate and the KL divergence from the base policy. When no inference time procedure is applied, the win rate corresponds to the standard win rate. By setting the transformation to be the identity, we achieve the optimal trade-off between win rate and KL divergence. We also note that using a logarithmic transformation recovers the well-known best of n distillation objective, which has been shown to be nearly optimal in terms of win rate. While these methods may lead to similar optimization goals, the algorithms used to solve them differ. We will present a unified algorithm for solving the transformed KL regularization for general transformations. In our results section, we will compare the outcomes when the transformation is set to the identity against other baseline approaches. We define a calibrated inference time procedure as one that has a mapping function allowing us to express the procedure in terms of the calibrated reward. Our findings indicate that for these calibrated procedures, the aligned policy derived from solving the transformed KL regularization has a win rate and KL divergence that are independent of the base policy and reward function. This property enables us to evaluate transformations by focusing on simple continuous language models that are easier to compute and simulate. In the following section, we will use best of n and worst of n as examples to show how this theorem helps us efficiently assess the trade-off between inference time win rate and KL divergence for different transformation functions, aiding us in finding suitable transformations in practical applications. Section Summary. In this section, we outline the properties of reward calibration, demonstrating that it preserves reward ordering and transforms reward distributions to a uniform distribution, which is crucial for designing inference time procedures. We also discuss how calibrated rewards can be applied in KL regularized reinforcement learning, allowing us to evaluate various transformation functions independently of the base policy and reward model, using examples like best of n and worst of n to illustrate our approach. Section: Finding better transformations for BON and WAN. In this section, we focus on two inference time procedures, best of n, BON, and worst of n, WAN. For the BON procedure, we generate n independent responses from a policy, which we denote as y1 through en. The final output is the response that receives the highest reward. In the WAN procedure, we also generate n independent responses from the same policy. However, here, the final output is the response that receives the lowest reward. We present a lemma that describes the distribution of outputs after applying these inference time procedures. For any n in continuous language model, the BON output is influenced by the reward of the responses, while the WAN output is determined by the lack of reward. It's important to note that the results for BON have been previously established. The lemma indicates that both BON and WAN are calibrated procedures. This means that for an aligned policy, the win rate during inference and the KL divergence from the base policy do not depend on the base policy or the reward model. Next, we outline the properties of the BON and WAN procedures. For any transformation function, we find a solution to the KL regularized reinforcement learning problem. We define a function that helps us calculate the win rates for both procedures over the base policy. Specifically, the win rate for BON is calculated using an integral that considers the transformation function, while the win rate for WAN is derived from a similar integral that reflects the opposite outcome. By adjusting the parameter in our KL regularized problem, we can create an alignment curve that shows the relationship between the inference time win rate and the KL divergence for various aligned policies. This allows us to compare the effectiveness of different transformation functions. In the remainder of this section, we will explore various types of transformations, including optimal transformations for standard win rates, exponential functions, and optimization-based transformations, and we will compute the alignment curves accordingly. Section Summary. In this section, we explore the best of n, BON, and worst of n, WAN, inference time procedures, where BON selects the response with the highest reward and WAN selects the one with the lowest reward from n independent samples. We derive formulas for their win rates and KL divergence, allowing us to analyze the performance of various transformation functions by plotting alignment curves based on these metrics. Section: Optimal reward transformations for standard win rate. In this section, we explore optimal reward transformations for the standard win rate. We note that the identity mapping and the logarithmic mapping used in best of n distillation are nearly optimal for this win rate, We aim to determine if these mappings remain effective when we consider inference time procedures. We derive an optimized reward transformation function. For calibrated inference time procedures like best of n and worst of n, we find that the optimal reward transformation is independent of the base policy. We can optimize for effective transformations using simple language models. Specifically, for any positive value, the transformation that achieves the best trade-off between win rate and KL divergence must meet certain equations. We can find this transformation by iteratively solving these equations. Next, we discuss exponential tilting for reward transformation. Inspired by the exponential tilting of loss functions, we consider an exponential transformation that adjusts based on the sign of a variable. This transformation helps optimize different quantiles of the reward. For positive values, it focuses on high quantiles, effectively recovering the maximum function for large positive values. Thus, we expect it to enhance the best of n inference time procedure. Conversely, for negative values, it targets lower quantiles, making it suitable for the worst of n procedure. In our results, we analyze an ideal continuous language model and compare various alignment objectives regarding inference time win rate and KL divergence across three procedures: standard, best of n, and worst of n. We generate trade-off curves by adjusting the strength of the regularizer. The objectives correspond to different transformations of the calibrated reward, including the identity mapping, logarithmic mapping, exponential tilting, and the optimized transformation derived from fixed points. In our first plot, we examine the standard win rate, where the identity mapping is known to be optimal. We observe that the logarithmic transformation also achieves a nearly optimal win rate, while other transformations fall short. For best of 2 and best of 4 win rates, we include the optimized transformation, which shows that the identity transformation is no longer the best choice. The optimized transformation provides the best trade-offs, with exponential transformations performing nearly as well. When we look at worst of 2 and worst of 4 win rates, the optimized transformation again yields the best results. Here, the exponential transformations for negative values also perform well. We find that both the identity and logarithmic transformations are suboptimal in these cases, with the logarithmic transformation performing better for worst of n compared to the identity transformation. These findings highlight the significance of considering inference time procedures in alignment tasks. We conclude that different exponential transformations are beneficial for various inference time procedures, which we will focus on in our practical experiments. Before proceeding to these experiments, we will present a practical algorithm for addressing the inference time KL regularized reinforcement learning optimization problem, which we will discuss in the next section. Section Summary. In this section, we explore optimal reward transformations for standard win rates, finding that identity and logarithmic mappings are nearly optimal, but their effectiveness varies with inference time procedures. We derive an optimized reward transformation function and introduce exponential tilting to enhance performance for different quantiles, demonstrating that tailored transformations significantly improve alignment across various inference time scenarios. Section: Control, Calibrate and Transform Reinforcement Learning. In this section, we introduce the control method, which serves as our solution for optimizing win rates during inference. We previously discussed that our approach can be broken down into 3 stages: reward calibration, reward transformation, and the standard KLRL solver. While we focused on reward transformation earlier, we will now concentrate on approximate empirical calibration. By combining this with reward transformation, we arrive at the final control algorithm. For empirical calibration, we take k-samples from the reference model for each prompt in our RL training data. We then sort the rewards for all responses and assign calibrated reward scores during RLHF training for each prompt response pair. Ideally, as k increases, the calibrated reward would align with the true calibrated reward, which we could use in our RL training objective through proximal policy optimization, PPO. However, Calculating this exact reward can be costly since it requires sampling and storing k-reward scores for each prompt and rollout in the KLRL solvers. To address this, we propose approximating the calibration curve using a stepwise function in the logarithmic domain, selecting p anchor points where we achieve zero calibration error at specific quantiles. To train our reward models, we utilize the anthropic helpfulness and harmlessness datasets, which consist of multi-turn dialogues between humans and digital assistants. These datasets provide two responses for each context, along with a label indicating human preference. We train our uncalibrated and calibrated reward models using the training splits of these datasets. The uncalibrated reward model is trained using a specific objective, while calibration occurs during the RL training process by sampling from the reference model. Both reward models are based on the POM2S model, which is fine-tuned on preferred responses. We then train the aligned policy model using KL regularized reinforcement learning. Since evaluating true rewards based on human annotations can be expensive, we automate this evaluation using a larger POM2M model. To assess improvements after RL training, we report win rates and specific win rate metrics, calculating these after applying inference time procedures on responses generated by the RL model compared to the base model. We experiment with different KL regularizer strengths and obtain a Pareto curve of KL divergence versus win rates. We first validate our hypothesis that reward models for real-world tasks are often miscalibrated. We measure the miscalibration of our reward model trained on the helpfulness dataset by computing scores for responses to random prompts. We then sort these scores and plot their ranks. If the model were perfectly calibrated, the points would align along a specific line, but we observe significant deviations for most prompts. We also measure the absolute error, A, between reward scores and their ranks, plotting the cumulative distribution function of the A for various calibration approximations. A well-calibrated model would show 0A, but we find that our reward scores are not calibrated. Using fixed polynomial transformations does not improve calibration, while a quantile-based calibration approach significantly reduces the calibration error. Section Summary. In this section, we introduce the control method for optimizing win rates during inference, which involves three stages: reward calibration, reward transformation, and the standard KLRL solver. We focus on approximate empirical calibration, demonstrating that our quantile-based approach significantly reduces calibration error compared to traditional methods, ultimately enhancing the performance of our reward models. Section: Calibrated rewards improve standard win rate. In this section, we examine how calibrated rewards enhance the standard win rate. To validate our InfAlign approach, we first assess performance without any inference time procedures. In this scenario, our optimization goal is the standard win rate. We compare control, which uses an identity transform, against other reward optimization methods known to be nearly optimal for win rate, like IPO and best-of-n distillation. We calibrated the reward model focusing on helpfulness and harmlessness, fine-tuning the base model on preferred responses using a specific algorithm with a parameter set to 1. Our findings indicate that calibrated reward optimization yields better win rate versus KL divergence trade-offs compared to IPO and best-of-n. We believe this improvement stems from a more effective calculation of win rate using samples from the base model, rather than relying on existing comparison data during KLRL. Additionally, we observe that the different reward transformations applied to the calibrated rewards perform similarly, supporting our theoretical results. We also note that reducing calibration error by increasing the number of anchors or adjusting the sample size leads to improved win rate versus KL trade-offs. Next, we focus on improving the best-of-n performance for the helpfulness objective in the anthropic dialogue dataset. We aim to optimize this performance through an exponential transformation of the calibrated rewards, measuring win rates against the best-of-n of the base policy model with 4 options. Our results show that calibration based on median rewards per prompt achieves an 8 to 12% increase in best-of-n win rates compared to the uncalibrated model. The exponential transformation of the calibrated reward outperforms other models, with a specific exponential factor of 10 yielding the best results in our simulations. We also confirm that these improvements are consistent across different values of n for the harmlessness objective. We aim to enhance the worst of n performance to ensure safety against adversarial attempts to exploit vulnerabilities. Here, we apply a negative exponential transformation. Our results indicate that calibration based on median rewards per prompt achieves a 4 to 9% increase in worst of n win rates compared to the uncalibrated model, with the negative transformation of the calibrated reward performing best. In terms of related work, we note that inference time computation has been utilized in recent studies to achieve better win rate versus KL divergence trade-offs from aligned models. Best of n is commonly used as an evaluation metric in various benchmarks, while worst of n is a strategy used by adversaries to elicit unsafe outputs from language models. Previous research has primarily focused on approximating inference time solutions during training, while our work operates under the assumption that no inference time procedure is applied, instead aiming to approximate it during training. We demonstrate that our theoretical framework encompasses IPO and best of n distillation as specific cases. We are inspired by recent studies that implement meta-generation procedures at inference time, such as chaining prompted models and problem decomposition. Our InfAlign framework is also influenced by complex inference time strategies that utilize transformation techniques, which have shown superior performance on challenging tasks. Our framework aims to achieve additional gains in aligning models with these future inference time procedures. Regarding reward miscalibration, we recognize that this issue has been extensively studied. The causes of reward hacking can be grouped into three main themes: reward underspecification, discrepancies between training and serving reward models, and dominant rewards due to ad hoc transformations. Our control method can be easily enhanced with data interventions to address these issues. Finally, we acknowledge the challenges posed by training reward models on wise preference data and using them as pointwise scorers during reinforcement learning, which can lead to inconsistencies. We share the motivation behind existing methods that incorporate wise preference data during offline reinforcement learning. Our approach emphasizes the need to calibrate rewards against the base policy we are aligning. When aligning language models for multiple objectives, aggregating rewards can lead to reward hacking. Techniques that calibrate against a reference reward can help mitigate this issue, but they often assume a logical and aggregation of all rewards, which can penalize underperformance. By employing exponential tilting to focus on high or low quantiles, we demonstrate that control with exponential reward transformation achieves near-optimal trade-offs between inference time win rate and KL divergence, surpassing methods like IPO that aim to optimize standard win rate versus KL divergence. We conclude that calibration is a crucial first step in grounding reward transformations based on the final inference time procedures applied.